let's give the formal definition of a rational function. We say a rational function is a function of the form r of x, which is equal to p of x divided by q of x, where p of x and q of x are polynomials, and q of x is not the zero polynomial. Now, what we mean is we're not saying that q of x can never be zero at any value of x. We're saying that there has to be at least one non-zero term down here for q of x. So here are some examples. 1 over x, 3x over 1/5 x squared plus 2. There are sometimes a polynomial will be in, or the rational function will be in different forms. For example, we know that x minus 3 times x plus 5, that will be a polynomial. If we multiply this out, this is going to be x squared plus 2x minus 15. And down here, if we multiply this out, we get minus x squared plus 7x minus 6x. So this would be plus x plus 42, I think. Okay, so this is a rational function, and in this expression, x plus 2 over x, it might not look like a rational function, but we can add these things by getting a common denominator. We can multiply and divide by x here. So this is going to be x over x squared plus 2. Okay, so that, sure enough, that is a rational function. So here, then these are not, the following are not rational functions, and I said not polynomials. Well, they're not rational functions either. So my bad. So we have here anything with a square root, that can't be a rational function. Basically, you can't have anything with a fractional exponent. So here, because this is this denominator, that's not a polynomial because of the cube root of x. Over here, this numerator is not a polynomial because of the negative 1/2 exponent. And of course, anything with an absolute value, that can't be a rational function. So none of these are rational functions because they have to be fractions of polynomials. Next thing I want to do is we want to talk briefly about finding the domain of a rational function, and we basically already know everything we have to know in regards to domains and rational functions. The two rules is you can't divide by 0, and you can't take the square root of a negative number. Well, there are no square roots, so you just have to worry about dividing by 0. So the domain of rational functions is everywhere the denominator polynomial is not 0. So the easiest way to do this is to take the denominator, set it equal to 0, and then find the solutions, and then throw out all those solutions, and everything else is in the domain. Okay, so for example 1a, we just set x squared minus 1 equals 0. Okay, this means x is going to be 1 or negative 1. So the domain would be all x not equal to 1 or negative 1. Okay, you can write this as an interval in interval notation as well, but that's the domain. Here on part B, the denominator is x squared plus 5. You try to set that equal 0, you get x squared is negative 5, so there's no solution here. At least not in the real numbers, and that's all we're considering our real numbers right now. So that means this is defined. We can plug any number in for x we want, so the domain is all reals. And then down here, 3x, the denominator is 3x squared plus x. Okay, we can factor out an x and get 3 plus x times 3 plus 1. Try again. Try again, Professor. Factor out the x, 3x plus 1 equals 0. Okay. So that's going to be, so either x is 0 or 3x plus 1 is 0, which means x will be negative 1/3. Okay. All right, so these are the two numbers that cannot be in the domain. So the domain would be all x not equal to 0 or negative 1/3. Okay. You'll notice that 0 is also makes the numerator 0 as well. That's going to be relevant later on, but not for finding the domain. For finding the domain, you just set the denominator equals 0 and proceed from there. To find intercepts of the graph of a rational function, that's really nothing new either. As I said to find the x-intercept, you set y equals 0. And to find the y-intercept, you set x equals 0. So in terms of this, if you set this expression equal to 0, the only way a fraction can be 0 is if the numerator is 0 and the denominator is not 0. So the x-intercepts are when the numerator is 0 and the denominator is not 0. And then the y-intercept is easy. You just plug in x equals, you plug in 0 for x, and if you get a number, that's the y-intercept. And if you don't get a number, if you get something undefined, then there's no y-intercept. So for example 2, part A, would be the x-intercepts. We set x plus, well, basically in all of these, it's a good idea to set the numerator equal to 0 and the denominator equal to 0. So, and it might actually be beneficial if we can factor. Let's factor now. So it's x plus 3 times x plus 1, x minus 1. Okay. So if you set x plus 3 equals 0, obviously the answer is negative 3. And then if you set the denominator equals 0, you get x equals 1 and negative 1. Okay. All right, so obviously you can negative 3 is not equal to 1 or negative 1. So the x-intercept is going to be at negative 3, 0. Okay. We don't use these numbers at all for the intercept. This just tells where the domain is not. And then for the y-intercept, if we plug in x equals 0, well, it looks like we get 0 plus 3 and 0 minus 1. So actually you get negative 3 as well. It's 0, negative 3, because you get 0 plus 3 over 0 squared minus 1 is equal to negative 3. So that's how you get this one. Let me pause the video and do the rest of these. In part B, you'll see that if you set the numerator equals 0, you get x equals negative 2. Okay, so and negative 2 does not make the denominator 0, so negative 2, 0 is the x-intercept. And if you plug 0 in here, you get 0 plus 2 over 0 plus 5. Well, that's 2/5, so it's 0, 2/5 would be the y-intercept. This x over 3x squared plus x, we just looked at this one. This is x over x times 3x plus 1. Let's make sure I do that correctly this time. Now, before you cancel out these x's, let me just understand that the 0, if you plug in 0 into the function, you'll still get something that's undefined. You still get 0 over 0. Okay, and because this is our original form, we know that 0 can't be in the domain. So so there is no y-intercept. The there's no y-intercept. And you'll also see if we try to set, the only time the numerator is 0 is when x is 0. But we just said that 0 is not in the domain. Okay, so this is going to be the case where there's no x-intercepts or y-intercepts. right? Basically, because if you plug 0 into here, you get something undefined. Now part D. Here we can see that the numerator is going to be 0 when these factors are 0. So that will be at -1 and 5. If you set each of these factors equal to 0, you get x equals -1 and 5. Okay, so -1 and none of these numbers makes the denominator 0. So -1, 0 and 5, 0 will be the x-intercepts. And the y-intercepts, what happens if we plug in 0? We get 3 times 0 plus 1 times 5 minus 0 over 0 plus 2, 0 minus 3. So this is going to be 3 times 1 times 5, that's 15. This is going to be 2 times -3, that's -6. I guess we could reduce this to -5 halves. Okay, so the y-intercept is going to be 0, -5 halves. All right. For the last one, let's find the y-intercept first, because that's going to be the easier one. 0 plus 1 minus 2 over 0 plus 3. That's going to be 1 minus 2/3, which I think is 1/3. So 0, 1/3 will be the y-intercept. And then to find the x-intercept, we have to do a little, you'll notice that this is not in the usual form. We could get a common denominator, but you don't have to. In this case, we can just set this whole expression equal to 0 and try to solve it. So we get x plus 1 minus 2 over x plus 3 equals 0. What I'm going to do is I'm going to multiply everything by x plus 3 to clear out the denominators. And so this becomes x plus 3 times x plus 1 minus 2. Because if we distribute the x plus 3, we have to multiply this by x plus 3 and this by x plus 3. And then, of course, this is 0. If we multiply this out, we get x squared plus 4x plus 3 minus 2 equals 0. And so x squared plus 4x plus 1 is 0. Now, this would be, this is a quadratic equation. You'll see that we can't factor this nicely, but we can use the quadratic formula because we're all experts on the quadratic formula now, hopefully, where this is a is 1, b is 4, and c is 1. And if you remember that the quadratic formula, minus b plus or minus the square root of b squared minus 4ac all over 2a. So this is going to be -4 plus or minus the square root of 4 squared minus 4 times 1 times 1 over 2 times 1, which is -4 plus or minus 16 minus 4 is 12 over 2. Okay, which I think it reduces to -2 plus or minus square root of 3. Okay, you can check. You can check if this reduces to this, or you can just leave it in this form. So there is x-intercepts. They're at 2 plus or minus, or -2 plus or minus square root 3, comma 0. Okay. Okay. And yes, things are a little bit different when you have a polynomial plus a fraction. And trust me, if we did it the other way, if we got a common denominator, we'd still have to use the quadratic formula. In fact, if we combined this, we'd still have to solve that quadratic equation. Okay, so hopefully you won't see anything too difficult like this. But again, all the work that we've done here we've seen before. We know how to find x-intercepts, set y equals 0, or set the function equals 0. And then for the y-intercept, we just plug in x equals 0.